So let's say we have this pipe of flowing water. And let's say we are trying to determine the amount of energy at this particular point. And let's say we determine the amount of energy at this particular point is 100 joules. Then something important to realize is if at this point there's 100 joules of energy, then therefore at this point there's also 100 joules of energy. And also at this point there's 100 joules of energy. And also at any other point, the amount of energy is 100 joules of energy. And this is simply conservation of energy. And this is Bernoulli's principle. And the key idea is if at a certain point there's 100 joules of energy, then you can choose any point in this flowing water. Literally, you can choose any arbitrary point, and the amount of energy at that point must equal 100 joules of energy. So let's say we wanted to determine the exact amount of energy at this particular point. How do we determine that amount of energy? Well, there are three forms of energy that make up the total energy at this particular point. There's the energy due to pressure, the pressure applied to this point. There's the kinetic energy of the water molecules moving with a certain velocity. And there's also the gravitational potential energy of these water molecules at this point. However, how do we determine the kinetic energy at this given point? Well, we know the equation for kinetic energy is 1/2 mass times velocity squared. So therefore, we would need to find the mass of the water molecules at this point and multiplied by the velocity of the water molecules at this point. And again, the velocity would get squared. However, how do we determine the amount of gravitational potential energy at this point? Well, we use this simple equation. We find the mass of the water molecules at this point, multiplied by g, the acceleration due to gravity, and multiplied by h, this height relative to a particular reference level that we would choose. However, something important to realize is when physicists deal with fluids, rather than dealing with masses, it's more convenient to deal with densities. And we know rho is the symbol for density. Because it's very difficult to measure the amount of mass of the water molecules here. However, we know the density, we can simply use the density. So that's much more convenient. So whenever physicists deal with fluid problems and fluid mechanics, rather than dealing with masses, they like to use densities. So now we know if we want to determine the amount of energy at this particular point, all we need to do is determine the pressure applied at this given point, add it to the total amount of kinetic energy at this given point, and add it to the total amount of gravitational potential energy at this given point. And if you determine all those values, you can determine the total amount of energy at this given point. And you could do that with any of these given points. If you wanted to find the total amount of energy at this particular point, again, find the pressure, find the kinetic energy, and find the gravitational potential energy. And once you know all those values, you can find the amount of total energy at this particular point. And it's the same thing with any of these other points. As long as you can determine these three values, you can determine the total amount of energy at a given point. So if you were to go through the values and find the total amount of energy at each of these given points, you would see that they all equal 100 joules. And this is simply conservation of energy. So you could choose any random arbitrary point, and if you were to find the pressure added to the kinetic energy and added to the gravitational potential energy, it would equal 100 joules. Because we know every single point must equal the same amount of total energy. So therefore, if we were to compare these 2 points, this point 2 and this point 3, we know they would both have the same amount of energy. This is simply conservation of energy. And we could actually set these two terms together. We could set the energy at this point and set it equal to the energy at this point, because we know the energy at each point is equal. And we know the energy at this point 2 is equal to all these values. And we know the energy at this point 3 is equal to all these values. And if both of these energies equal each other, then both of these must equal each other. And this is true for any of these points. You could set the amount of energy at this point and set it equal to the amount of energy at this point, and set that equal to the amount of energy at this point. And you could choose any arbitrary point, and you know the amount of energy at that point must equal the amount of energy at any other arbitrary point. However, in order to truly understand Bernoulli's principle, there's another equation you need to be familiar with. So, if you have a flowing liquid, and if you were to find the cross-sectional area of one region and multiply it by the velocity of the water molecules moving through that region, that product would have to equal the cross-sectional area of any other region multiplied by the velocity of the water molecules moving through that region. And that product would have to equal the cross-sectional area of any other region multiplied by the velocity of the water molecules moving through that region. So this principle is referred to as the continuity principle. And you could choose any region. For example, you could find the cross-sectional area of this region and multiply it by the velocity of the water molecules moving through this region, and that product would have to equal the product at any other region. So again, this is referred to as the continuity principle. For example, let's say the cross-sectional area of this region is 1 meter squared. However, let's say the cross-sectional area at this region is 10 times greater, is 10 meters squared. Well, if the cross-sectional area is 10 times greater at this point 3, therefore the velocity must be 10 times smaller, because that's the only way for these two products to equal each other. So if we were to multiply and find the product of these two terms, we would get 10 meters cubed per second. And if you were to analyze these units, this is units of flow. This is volume per second. This tells you the volume of liquid moving through that region per second. So this continuity equation tells us the flow. This product tells us the flow. So this continuity equation tells us the flow going through this region equals the flow going through this region, which equals the flow going through this region, which equals the flow going through any other region. If you find the cross-sectional area and multiplied by the velocity of the water molecules, that gives you the flow, the volume flowing per second. And really, this is just conservation of mass. For example, let's say the flow moving through this region was 20 meters cubed per second. However, let's say the flow moving through this region was only 10 meters cubed per second. Well, this wouldn't make sense, because if 20 meters cubed per second flow was going through this region, but only 10 meters cubed was going through this region, then we would have water accumulating in this region, and this region would explode, because more water is flowing in than is flowing out. We have 20 meters cubed flowing in, but only 10 meters cubed flowing out. That doesn't make sense. We have more going in than is going out, so water would accumulate and this would explode. So this would not make sense. So therefore, the flow going through any region has to equal the flow going through another region. If the flow entering this region is 10 meters cubed per second, then the flow leaving this region must be 10 meters cubed per second. This is the continuity principle. So an important implication of this continuity principle is the smaller the cross-sectional area, the larger the velocity. Because again, based on this continuity principle, if we have a small cross-sectional area, we have to have a large velocity, so this flow equals the flow at this region. And if we have a large cross-sectional area, we must have a very small velocity, because that's the only way for these two flows to equal each other. So therefore, essentially, the smaller the cross-sectional area, the larger the velocity, and that keeps the flow consistent. And therefore, the smaller the cross-sectional area, the larger the velocity, the larger the kinetic energy, because we know this is the term that equals the kinetic energy. So therefore, the larger the velocity, the larger the kinetic energy. And we know the smaller the cross-sectional area, the larger the velocity. Hence, the smaller the cross-sectional area, the larger the velocity, the larger the kinetic energy. So therefore, the kinetic energy at this point 2 is greater than the kinetic energy at this point 3. So now that we understand Bernoulli's principle, let's try an example. Let's compare the energy at this point 2 and compare it to the energy at this point 3. Well, something we need to realize is that the gravitational potential energy at both of these points is equal. Because we know if we had a reference level, they both have the same height. So therefore, the gravitational potential energy at point 2 equals the gravitational potential energy at point 3. They both have the same height from a reference level. So therefore, we know the gravitational potential term has to equal for both of these sides. However, based on the continuity principle, we know because we have a smaller cross-sectional area at point 2, we have to have a larger velocity at point 2. So therefore, because we have a larger velocity at point 2, we have a larger kinetic energy at point 2. So therefore, we know the kinetic energy at this point 2 is larger than the kinetic energy at this point 3. However, if we know both sides have the same gravitational potential energy. Point 2 has the same gravitational potential energy as point 3. However, we know point 2 has a larger kinetic energy than point 3. However, we know the total amount of energy at point 2 has to equal the total amount of energy at point 3. So the only way for these two total energies to equal each other is if point 3 has a larger pressure than point 2. So therefore, we know this point 3 has a larger pressure than point 2. And that's the only way for this total energy to equal each other. And we know the essence of Bernoulli's principle is if you were to take one point and find the total energy, it would have to equal the total energy at any other given point. So therefore, we were able to infer that the pressure at point 3 has to be larger than the pressure at point 2 because that's the only way for these two energies to equal each other. However, let's try another example. Let's compare the energy at point 4 and compare it to the energy at this point 5. Well, clearly, we can see that the cross-sectional area is the same. So because point 4 and point 5 both have the same cross-sectional area, they'll both have the same velocity. And that way they'll both have the same flow. So because they both have the same velocity, we know they both have the same kinetic energy. So therefore, the kinetic energy of the water molecules at point 4 equals the kinetic energy of the water molecules at point 5. So both these kinetic energies equal each other. However, we can clearly see that this point 4 is at a higher region than this point 5. So if we had a reference level, we would see that the gravitational potential energy at point 4 is higher than the gravitational potential energy at point 5. So we realize the gravitational potential energy at point 4 is larger than the gravitational potential energy at point 5. However, we know the total energy at point 4 has to equal the total energy at point 5. So therefore, if they both have the same kinetic energy, however, point 4 has a larger gravitational potential energy than point 5, therefore we know point 4 must have a smaller pressure energy compared to point 5, and point 5 must have a larger pressure energy than point 4. Because that's the only way for the total energy at point 4 to equal the total energy at point 5. So, understanding these concepts of Bernoulli's principle, we're able to infer that the pressure energy at point 5 is larger than the pressure energy at point 4. So, the key point of Bernoulli's principle is if you were to find the total energy at any given point, that total energy would have to equal the total energy at any other given point. And we know how to determine the total energy at a given point. If we want to determine the total energy at this point 4, we need to find the pressure at point 4, added to the kinetic energy of the water molecules at point 4, and added to the gravitational potential energy of the water molecules at point 4. And because all these energies must equal, we can set all these points equal to each other. The total energy at point 1 has to equal the total energy at point 2, which has to equal the total energy at point 3, and etc. So this is Bernoulli's principle.